Hello, I'd like to introduce Paul Khuong, who'll be discussing prefetching and searching. So searching on sorted arrays, a very fundamental common operation for a lot of software. Paul currently works at AppNexus, where he helps with scalability and reliability, and he previously hacked on the Steelbank Common Lisp implementation compiler.
Thank you. Right. So prefetching and searching. I'm presenting basically one of the results that we have in this paper with Pat Morin. So if you don't want to read the paper, like the punchline is, we don't really care about cache misses anymore for searches in sorted arrays. Just prefetch this out of the memory subsystem. Right? But this is not the main topic of this talk. It's more about how we got to that conclusion, which I think is the interesting part. So some history. A couple of years ago, I was working on my PhD in operations research, and I was representing a lot of hyperarcs as a sorted struct of array of small ints. So, that way I get density, and I can easily exploit normal algorithms to search in these arrays, like, I don't know, binary search. And I got like that kind of thing out of it. A Lagrangian-based branch and bound algorithm for a 2-level uncapacitated facility location problem with single assignment constraints. It was really great, and I needed a break from all that. So I did some literature review on how do you search in an array of ints. What I found was papers with code. The code was what it was. It was such that there's no way I could trust their benchmarks. So that was great, right? Because the whole point of their thing is to say, well, this new tweak here was so much more faster on real machines, even though theory says they're the same. Well, your code is not very trustworthy, so I don't know what to make of your benchmarks. And then there was paper without code. That was even better, right? There's no code. I have no idea what they screwed up this time. And then there was this one thing that seemed interesting in theory. It's the MD-Bose layout, which in theory is kind of adaptive to whatever is the size of your cache lines. So that was great. But again, none of the benchmark that says, oh, this really works well on large data sets were that trustworthy. So what do I do next? Well, I do some, right. And there was also, everyone seemed to agree on these kind of rule of thumbs that for small arrays, you should probably use just linear search, right? Because linear search is so much simpler than any kind of sorted search. If it's large-ish, use the breadth-first search algorithm where you kind of reorder your thing in heap order. And if it's very large, at some point, it might be, depending on the paper, a couple megs to a couple gigs, then you switch to the MD-Bose layout. And I'm not sure that's true, right? Because you look at their experiments, and they're well, it's always powers of 2. Why is it always powers of 2? Because they're well, really what we're doing here is finding different ways to represent full binary trees, which is cool, right? Because any full binary tree is going to be of size 2 to the k minus 1. The only issue is that if you're of a size 2 to the k minus 1, you're going to get into a lot of cache aliasing issues. So now, do you know if the result that you're reporting is actually an implementation, an improvement that you brought with your new layout, or are you just avoiding aliasing issues that don't really happen in real life because few data sets are exactly 2 to the k or 2 to the k minus 1. Some algorithms are harder to screw up than others, right? If you write a heap order search, you go to 2 to the I plus 1 or plus 2. So you do 2 to the I plus 1 plus the result of a comparison in C. And there's so little things that you can screw up in there, you'll get decent code out of it anyway. But if you look at, say, an MD-Bose search or a binary search, there's so many ways that you can, kind of pessimize your code by trying to be clever that I don't know if when you see consistently that, say, BFS is faster than just searching a sorted array, is that because consistently BFS is easier to implement? And then I think It's important to remember that a lot of these papers either are old or are from academia where they don't have any money, so they have to work with 15-year-old hardware. So they have very, very small TLB, so translation loci buffers. And that means that there's so much more pressure on avoiding TLB misses during page translation. And that, I think, is a key point. Because if you look at the literature, they're all like, well, if you use cache obvious algorithm, it's going to be much faster because you don't have to tune for the size of your caches. But that's not true for complete binary, like for complete search trees. Regardless of what you do, what's going to stay in cache is the top of your search tree. Everything else is just going to be cold because there's not enough space. Really, what matters is the block size. And if you're only looking at data caches, it's always 64 bytes. That's great. Everyone can handle 64 bytes. Just do a search tree where each node is 64 bytes and you're good to go. But when you need to handle address translation as well, then you have two kind of layers of caching. The first one is the data caches with 64 bytes. And then you have the TLB at 4K or 2 megs or 1 gig now. And that's hard to do correctly. And I think that's really what happened with cache obliviousness is that they got that for free. They did not realize that was the reason they saw such speed ups in search. Anyway, so it was time for non-research research. So research about not my actual research. And I got, so first, stop doing binary search wrong. There's no branch to predict or mispredict in binary search. It's just a conditional move. And now if you do that correctly, then you have binary search is actually faster than linear search on like decent enough arrays. Also, stop doing these microbenchmarks on powers of 2, because then you hit this very pathological case for binary search that never happens in practice, because it turns out that when you divide a power of 2 by 2, you still get a power of 2. So everything ends up being a multiple of 4K, which is the mod that you use to hash your L1. So everything goes to the same cache line, and obviously that's not going to end up very well for you. And then there's this other thing that happens, like they say, well, the breadth-first layout is more efficient because the top of the tree is contiguous. I'm like, that is not how caches work. They don't care like what the addresses are as long as they're in the same cache line. But apart from that, it's pretty much like a hash table, right? So that just, what? There's no way that's right. I never got to far enough to explain why, but that's where I was back then when I decided I had to graduate and actually work on my research. So what I do then is binary search is definitely better than what the papers claim. How good? No clue. And then this time, all I wanted to do was play with the MD Bullis layout. All I know is I don't know if it's as good as they say, but I'm pretty sure that I can't trust anything they told me so far. That was great. Then I found a job. That was much better. And then come 2015, I see this thing on Hacker News where Pat Morin has a project that is very relevant to my interests. And it's interesting because it has code. It has code under an open source license. Pat is still gathering results. And Pat has done all the hard part, like permuting the arrays so that you can search in them. Now I only have to do the fun part, which is making the searches fast. So I look at the code and I'm like, oh, right, academia. So this is like one of the examples of how you can kind of screw up binary search. So the first one is, yes, there's an overflow. Right, everyone knows that one. But I think the important one is, first, it tries to find an exact match when, that's never going to save you more than like one iteration on average. And it manages to insert ifs in what should just be a conditional move. So that's great. And then you see, like I said, breadth-first search, you can't screw it up, right? Well, this is what I saw. So there's also an if in there, and it's also looking for an exact match, but whatever. I'm not that interested in the small and for now. I just want to see what happens when we get out of cache and we hit like very large data sets. So let's run the original code on my machine that I know it's doing. So it's an unloaded box. It has enough RAM. I can control NUMA locality to make sure it's all on the local memory, and I can play around with page sizes to kind of see how much of the effects that we see is from TLB misses versus actually just doing better with the caches. So there's a bunch of algorithms and a bunch of data size. Turns out, well, it's pretty much all the same regardless of the page size. So let's look at 1 gig pages. That way we don't have to worry about too many things at the same time. Like there's no TLB involved anymore pretty much, right? Okay, so now we have, all right, what do we have here? This is gonna be interesting. I never rehearsed this, I was sick all week. So we have binary search in red. Then we have B tree, that's B plus 1 tree where the B is set so that it's exactly 1 cache line. Eitzinger, that's BFS, and then VB, that's the MDBOS layout. And then we have 4 data sizes, 32-bit int, 64-bit int, and 128-bit ints. So what do we see? Well, mostly we see they're pretty much all the same for small sizes, except for MDBOS, which is so much slower. That's kind of expected, given that we've seen that the code wasn't amazing. But I think the interesting part is when we get out of L3 and we see what happens when you hit main memory. So binary search becomes much slower than everything else. It's like each iteration, each cache miss is more expensive, which makes sense for the MDBOS and the B tree layout because they get so much more information out of each cache miss, right? If you have 4-byte UN32, then you have 16 of them in the cache line. So you do 4 iterations of your search before you have to switch to the next cache line. That's great. What is kind of interesting, though, is that it's also true for the breadth-first search. And breadth-first search, once you're out of L3, definitely only hits 1 element out of each cache line. So what is going on here? I think it's important then to go back to the claim as to why breadth-first search is faster than binary search here. In theory, it's because it fits more of the stuff in cache. If that were true, then what we would see is that they would both have the same in-cache regime. Then at some point they split where binary search starts hitting main memory, while breadth-first search still keeps doing the same. And then at some point it hits main memory again. And once they're both in the main memory regime, they should be at about the same slope in terms of how much of a slowdown it is to do 1 more cache miss because they're both doing 1 cache miss per iteration. It turns out they're not, right? You can see that this is true regardless of the key size. Cache misses are faster if you're doing breadth-first search. That's what we see here, right? Again, this is what we see with binary search. First, you have L1 and L2, pretty steady slope. Then L3, a bit heavier slope. And then much steeper slope for when you hit main memory. Breadth-first search. Well, you have this weird smooth thing that goes on until about L2-ish, a bit more than L2, and then a slow, kind of not clear what this is, concave curve. So first thought is, well, the only way to make cache misses cheaper is to just prefetch, and now your cache miss is actually not a miss. So let's disable prefetching, do some write MSR, hope you don't mess up your computer, and run the experiments again. Well, this is exactly the same graph. There is no impact. Like, the hardware prefetcher does not help any of these algorithms. So again, this is what we have so far. From our observations, if you do breadth-first search, your L1 misses are faster than if you do binary search. And it's not prefetching. So, like, mind blown here. So I'm stuck. I'm like, what am I going to do here? There's no way this makes any sense. I might as well just make it faster because that's what I'm good at, and perhaps something will fall out of that. So this is what a branch-free binary search looks like. All right, you divide by 2 with a shift, you do 1 conditional move, and then you subtract, and then go back to your loop. Very simple. And this is what a branch-free breadth-first search looks like. What you do is, well, You do one little bit of arithmetic, conditional move, and that's your while loop. The decoding part with built-in find first set is very clever. Not my idea. That was Pat's find, very cool. If you go into the paper, he describes exactly what's going on here. So we make it faster. And now finally we see something that makes sense at the low end where there's some separation. Binary search is faster for small arrays. BFS is a bit slower, but not dramatically so, than B-tree and VEB. And something else makes more sense. Now the slope for Eitinger, so breadth first search, and for binary search in red are pretty much the same when we're in main memory. Finally, now that I've made things faster, it makes sense, and we see that L3 misses cost the same if you do binary search of breadth first search. Or is it, right? Is it actually faster? Well, if you go back to the original code, we see that at the very high end for large arrays, even binary search is at most about 1.2 seconds for a couple million iterations. Now we go to the fast code, and it's 2 seconds. What? So I've made things make more sense in the regime that we're trying to understand, which is when you're out of cache, but it's also slower, so that's great, right? So Pat and I are like, well, this doesn't make any sense. What are we going to do? We can publish this. They're just going to shoot so many holes through this. So then I'm on the train, trying to go to work, and I get this email. It's just a wall of copy and paste from perf output. And I can't make sense of this. I'm just waiting until I go home. And this is what I get. The important part has a red arrow next to it, that we spend much more time waiting for data for the comparison. So that's good, right? Except it's also, we spend much more time in real time. So interesting, why is the data for comparison so much slower to come in, right? Right, I know what this is. It's not prefetching, it's just branch prediction. By converting conditional branches to conditional move, we took a control dependency, we turned it into a data dependency. Control dependencies are cool because they get predicted. So that's great. Control dependencies is not so cool because they get mispredicted, which is what usually happens 50% of the time when you do a search in a sorted array. So we try to get rid of them, right? Mispredictions are bad. Well, so if you go back to Norvig's table of latencies, mispredictions are bad, but what's even worse is a cache miss when you have to go to main memory. That's orders of magnitude slower. So what's happening here is that, let's say with binary search, the CPU is kind of trying to guess if you're going left or right, and 50% of the time it'll guess right, it'll guess correctly, and you'll have prefetched the correct data, and your search is faster just by accident. So that's kind of standard. So what's happening with breadth first search, though? It should be the same 50% hit rate. But if you think about the layout for breadth first search, one node in breadth first search has 16 great-great-grandchildren. If you look into the array, these 16 great-great-grandchildren are all contiguous in the array. So regardless of how you get there, of if you choose left, right, or whichever way, you'll always hit the same cache line. So the CPU here, by trying to predict and being wrong, or sometimes being right, still ends up predicting the correct cache lines 4 iterations ahead of time. And that's a ton of time to prefetch data, right? So sanity restored. Sometimes if you don't know what you're doing, branches make code faster, I guess. So what do we do? Well, we added explicit prefetching. And now we see that the branch-free code with prefetching runs much faster than the branchy code. And at last, the lower latency of breadth first search decache misses is explained. It's that sometimes you get prefetching for free, not from the prefetcher, but simply for branch prediction. Wow. Well, I should have run through this at least once. All right, so This is the code. Just add this one line of prefetching, and suddenly you get exactly the same performance for large data sets with branch forget, branch full, Redfoot search. So, summary. This is where I start ranting about microbenchmarks. Like if you run a microbenchmark, it's usually not to determine which method is faster. It's because you want to make something faster that happens to use either one of these methods. So really settling for which one is the fastest doesn't make any sense, right? You should at least know why, because if you choose it, then you want to know when you should make a different choice. Like what part of the environment makes it so that A is faster than B for your data set. So don't just ask which one is faster, but it's which is faster and why is it faster, what makes it faster. So that gives you an explanation that you can now test. And you should test it because it's very easy to get wrong. Like we did several times here. We had, all right, we noticed this must be prefetching. Shit, no, it's not prefetching. What is it? And that's how you get to improvements, right? So micro benchmarks, again, you're trying to improve a system by choosing the right method A or B, right? So here you say, instead of choosing A or B, choose C, which is a new method, which is even faster than A or B that we got to because we finally tried to understood why A was faster than B. And finally, like, there was this great column by somewhat with my initials, I put an H instead of a V, where they introduced varnish. And then they said something like, oh, it's cool, useless. They don't teach you about caches. They always teach you about O of N analysis, but they don't know what real machines look like. Like, dude, we've had theoretical machines and performance models that are cache aware for more than 40 years. Like this, I don't know where this comes from. So we have theoretical machines for caches. We don't really have any such kind of theoretical model for prefetching machines. Perhaps we should have them. I hope you have questions.
Hello? Yeah, I was wondering if you also tried the prefetching on any of the other layouts. Like, are you certain that it wouldn't work well because of the cache aliasing?
Right, so we did prefetching on binary search as well, which helped with the fact that branch-free binary search is slower on large data sets, and it was all consistently faster. That was great. For other, not really for other layouts, and the reason is that you only really know what cache line you're going to hit at the very end of your small local search. And before then, you have to choose between 17 children, right? You can't prefetch 17 cache lines. That's not realistic. So not really.
Thanks.
Yeah. Do your programmer's delight talk. The one just.
Do you still have the slides?
Do I still have? Yeah.
You do.
Programmersdelight.org.
All right.
So here's a slide that provides some background on essentially.
Do you Windows?
No, but it's probably F11. It's Chrome.
F11? No. F10, F11?
Oh.
Nice. All right. So programmer's delight.
.org.
All right. Yeah. Just go there.
So for many of us have implemented binary search in one form or another. Most people get it wrong. So this is essentially a follow-up from, this is the beginning of Paul's work in binary search. It's a talk he gave a while ago at a meetup we have here in New York. We have 45 minutes to the next talk. So.
What? I'm sorry. Well, I did like half an hour.
There you go.
All right, thank you. Right, so I mentioned this before, like binary search is so easy to get wrong. I don't know why, right? Because it's probably the first one that they teach you in school. It should be easy to get right. Well, it's easy to make it correct. It's hard to make it work as well as it should work. So this is how we get to these myths, like, oh, linear search is faster than binary search for small n because branches is so expensive. And then fancy layout worked better because caches, but like I said, most of that is misinterpreted data. Anyways, so the first one is, right, you want to make sure that your binary search doesn't have any branch in it. That way you don't get any misprediction. I don't think we can. All right. Right. Because this is what happens when you introduce branches in a search. As you do random searches, you see that the variance increases. So the y-axis here is time and cycles. Then you have different sizes of vectors. And you can kind of see the time it takes as the number of iterations increases. So these are all like different forms of linear search, and then you have binary search at the end, which is always very tight, which is what you're looking for if you work in a latency-sensitive system, right? You don't necessarily care about the fastest average case performance, but you want to make sure that like 99 percentile is fast. You really want to make sure that you don't sometimes get slow, because then you get into weird queuing effects and just it all snowballs into nothing's working anymore. So how do you get there? Well, first, you don't look for early matches. If you see something like this, like, oh yeah, sometimes like I might just find the element at the top of the tree. Why should I do this the rest of the search? Well, you should probably run the stats. And then you'll realize that that almost never happens, right? Half of your data is at the leaves. Only 1/4 is just one level above. So that 1/4 of the time, you'll say perhaps one iteration. And then 1/8 is 2 layers above. So that's the usual telescopic sum. So you're saving one iteration at the end of the day. Not great. Do not do this. The amount of time that you waste on just variance and branch misprediction more than dominates what you might save a small percentage at a time. Now, you also don't try to adjust bounds too tightly. This is what all the STLs do. Like, oh, I want to save 0.001 comparisons sometimes by doing this thing where, all right, so I'm going to divide my search range by half sometimes. Or if I know that the element I'm looking for is greater than or equal to my midpoint, I can kind of reduce it by even more. If you do the math again, you'll find that you're saving, I don't know, not even a fraction of an iteration most of the time. So no clue where that comes from. And then you do not want to do both, right? That's classic libc stuff, where they do a three-way search, and then like, okay, well, is it less than, and do this thing? Is it greater than? Then I can clearly save a lot of work by just adjusting my midpoint by one element. And then otherwise, make sure I get that lucky case right and return immediately out of my search loop. Also very much not great. Do not recommend that one. So this is what a simple binary search looks like. Just don't try to be clever. Do it like this. It'll work. What's happening here? So one key element is that it's always OK to have a search range that's slightly bigger than what you should have due to binary search, right? Because it's always OK to binary search over a longer range. Your recursion is still correct. The only thing you want to avoid is out-of-bound accesses. So what you can do is have a static schedule for the size of each subrange that is independent of the data in your array. That makes everything easier to compute, and that means that the number of loops that your search goes through is independent of the data, so it's very easy to predict. It's always a constant number if you have the same size for an array. And there are actually branch predictors that do that now. If you run a decent enough Intel processor, they'll do things like, oh yeah, this loop usually runs 5 times, so I'm going to count it to 5 and then abort out. So how do you get there? Well, you find what is n over 2. Like, all right, that's greater than 0, so n is greater than 1. So I have something to search over. I'm going to find my midpoint, do my comparison. And that's when you update the low point of your search range, and then you update the size of your search range by subtracting n over 1. So now remember, half was truncated because that's how C works. So n minus half means that it's n over 1. You take the ceiling, and so the recursion is always correct. Like, that is so simple, you could actually vectorize it if you have AVEX2 and all the necessary gather instructions. So that's great, right? You could actually vectorize binary search. And this is what happens if you have like a not stupid compiler. Like, even GCC gets this right. So some address computation, you do comparison, a C move, you subtract, and you do shift to divide by 2, and if it's non-zero, you do back. How does it work in a real machine? I think it's important to remember that real machines are kind of like data flow machines. So you want to unroll this loop and look at the data flow graph. And it's nice because you kind of see two parallel critical sequences. Like, one of the critical paths, one is clearly shorter than the other, so it's actually not a critical path. It doesn't matter. And the one that matters is the one on the left. And it's on the order of, let's see, what did I say? 1, 1, 1, and about 3-ish cycles plus the memory load, which hopefully is from cache. Otherwise, it's not, and still, there's not much you can do. So each iteration is on the order of 4 cycles plus your memory accesses. It's going to be hard to do much better than that. All right, time to microbenchmark this stuff. We got the branchy stuff from the STL, right? We got libc, which is branchy and looks for early termination. We have this weird case where you don't do branches, but you look for early termination just in case. Completeness sake, I don't know anyone who does that. And then you have the simple binary search, the simplest one, I think, which happens to also be the more efficient one with conditional moves. So we do this on 32-bit ints. They're random, and this is averages for 128 lookups. You get median and low top percentiles as shaded areas. So what happens first when you always look for the same element, is it? Yep. What is going on there? What? First, yes. Oh, right. Sorry. So when you would end at the first iteration with early termination, then yes, early termination works. Otherwise, you don't get it. If you end at the last iteration, you see that, well, obviously looking for early termination doesn't help, but it's not much slower than anything else. What happens if you now either end at the first or at the last iteration? That's bimodal. And now you see that the variance goes through the roof for anything that looks for early termination. Not great. Well, the simple binary search is now always consistent and pretty much always the faster option. And then we do random searches and intersections. Intersection is basically searching for increasing integers. And so what you see is that basically, if you stick to the simple one, yes, you'll sometimes miss very easy cases where you do only one iteration, but that's the only thing that you miss. And how often does it happen that you're looking exactly for the median in your array? If I know I'm looking for the median, I'm just going to go there. Otherwise, it almost never happens. All right, the other one I quickly mentioned in my previous talk was, don't do searches over 2 to the k minus 1 items because we're going to get into huge cache aliasing issues, right? Because this is what your endpoint looks like in hex. You just divide by 2, but it's always a power of 2. This is the reason this hurts is kind of weird, right? It's because L1 caches and Intel RVIPT, right? virtually index physically tag YRDVIPT because address translation is slow. So you want to figure out what hash bucket in your cache to go into without doing address translation. So now you can do both at the same time, right? So the only way to do that is to say, well, the page size on x86 is never smaller than 4K. So I'm going to do something mod 4K to find my cache line or my cache bucket. And then I'm going to disambiguate with the physical address once I have it. So if everything is the same mod 4K, you always go into the same hash bucket in your L1 cache, and you're kind of not using a lot of it. So don't do that. So that means either run proper micro benchmarks, where you don't just do powers of 2, because that's like, who does that in real life? Or don't do that by not doing exactly the midpoint, like offset by a small multiplicative factor, or just do three-way search. So instead of doing binary search with one midpoint, you can do the same by splitting at 1/3 and 2/3, and then you go left, center, or right. And that's also interesting because you get more memory level parallelism that way, because you do 2 loads at each iteration. It's kind of wasteful because you do 2 loads, but you only divide by 3 instead of dividing by 4, as you would with binary search. But if you assume it's going to happen in parallel, it's kind of for free anyway. So it does happen. Like, there's one reason I know in like real life that you'd have power of 2 size arrays is if you do like something like an LSM, when you just do powers of 2 and then you merge 2 arrays that are powers of 2, and you get what? Another power of 2 array. I don't know if I want to go into this one. I do? All right. So this is the main use at AppNexus for binary search. Like, you might kind of wonder, who cares? Like, why do we want to make searching and sorted arrays faster? And that's it. So AppNexus runs a bidder and real-time bidding for ads. So that means we get some info about someone who goes on a website, and we have to quickly determine what kind of ad we want to show and how much we want to pay for that ad. How much we want to pay is an interesting question, but turns out that most of the work in RTB is finding people you want to show ad to, because a lot of them are not people. They're bots, and a lot of them are not people that you want to show your ad to. Like, say I am Chrysler. I want to show ads for certain cars to young males that are frequent users of AutoTrader or something like that, right? There aren't that many of them. So most bid requests that I will see, I just want to drop on the floor as soon as I can. That's kind of the hard part of RTB, like real-time bidding for ads, is that most of the stuff you see, you have to parse it only to figure out that you actually don't want to do anything with it. So how we do this is we run a lot of campaigns at the same time. So even if you're not interested in it, we'll know someone who's interested in it. So that's the hard part, finding out who's interested in the bid request that we just saw. And the way we do it is we kind of have this huge sparse bit matrix of criteria that each campaign, each thing that we want to show an ad for, is interested in. Then you have a sparse bit vector that is like a one-hot encoding of what is on the bid request. So it's stuff like, oh yeah, this is this website. This is someone we think is between 25 and 35, and like they're using Chrome. And from that, we get a bunch of bit sets that we can end together and figure out with the normal. You turn your complex Boolean query into bitwise operations over column stuff to then get a 0-1 vector of, yes, I think I'm interested in this bid request, or no, I don't think this campaign is interested in that bid request. So our inner loop then is just pretty much a binary search. That's great. There's a bunch of people who always suggest, well, why don't you just increase the lower bound as you go along in your search, because you know that the indices you're looking for are monotonically increasing, right? Turns out that's not useful, because it means that you always search over different bounds. So your binary search will go at different addresses, and now you're just randomly causing more cache misses. Don't do that stuff. And yeah, if you mention that to one of the D people, they always say, oh, well, we have this search thing in D that does exponential search. You should do it, right? Like, yeah, well, it's great, but it's a lot of extra code, right? It's kind of much more complicated than just a B search. And B search is itself adaptive to small changes because you only pay cache misses when you kind of go very far away from the previous hit. And what is this? All right, nice. I can definitely show this because it's all data that's not true anymore. So this is the impact on the gather phase. So that's the part that does the sparse bit matrix multiply of, what is this? At the top, you have what happens when you always increase the lower bound of your binary search. This is what? Almost like 50% slower than just not doing anything special. Don't do that thing at all. For sure, don't. Then you have branch-free search in the middle. And then everything is kind of all in the same bin. Like, doesn't really matter what you do at that point. It's like kind of 10% difference. And why is that? Well, like I said, that's because if you do binary search over a sorted array and you don't update the bounds, you kind of get a decent finger search for free. So, yay. All right. That's all I got here. I don't even know what this is. All right. And that's it, right? So binary search works well on normal computers, just don't mess it up. All right, thank you.